This set of notes is going to give an overview of some basic stuff that we need to know for nuclear chemistry as we move into that. So nuclear chemistry is the study of reactions that are caused by a change in the nucleus of an atom to become a new element. So it involves just the protons and neutrons. So outside of this unit, when we talk about equations, we're going to be talking about chemical equations. What elements and the amount of them that we start with, we have to end with. In a nuclear equation, it's a little bit of a different set of rules where we're going to see that elements actually change from one element to another by emitting different particles, and we'll talk about some different variations of that as well. So you can see the notation looks different. You're going to see extra numbers involved with the symbols, which are your mass numbers and your charges, and we'll get into that later in this unit. All right, so why does this even happen? So part of it has to do with two guidelines we follow. So the large atom rule deals with elements that have an atomic number greater than 82. Those are naturally radioactive. They don't have any stable isotopes, and this is due to an unstable proton to neutron ratio. The small atom rule is that elements with an atomic number of 82 or less have at least one stable isotope, with the exception of technetium, and that's because of its stable proton to neutron ratio. So when you have questions about why a certain isotope would be naturally radioactive or stable, it's going to have to do with whether or not that proton to neutron ratio is stable or not. So what happens when we do have something with an unstable nucleus? That nuclei will naturally or spontaneously give off radioactive particles and will change from one element to another. And that process is called transmutation, when it's going to change into a new element. This only happens when we talk about nuclear chemistry. So you can see here in this reaction, they're just depicting the nuclei. You have uranium, and it's going to transmute into thorium by giving off what's called an alpha particle, which is just the same thing as a helium nucleus, which is where the Ag comes in. So there's different types of radiation that get released by unstable nuclei. So the ones that we deal with, which will be on table O, is alpha particles, beta, positron, and gamma rays. The first three are actual particles. Gamma is just pure energy. Some of the things we're going to talk about, we're going to find on table O. One thing you do have to memorize is their strength. So alpha has the weakest strength. We can stop it with just simply a sheet of paper. Beta and positron decay is about medium strength. It will go through the paper, but you can stop it with, say, a piece of wood. And gamma radiation has the strongest, highest strength or power. And that can go through the piece of wood, but can get stopped by like concrete or like a sample of lead. So you're going to see we're using table N and O quite a bit in this unit. Table N right now gives us the decay mode. So this lists different radioisotopes, so radioactive isotopes, and shows what type of decay they go through. You look at the symbol, so say carbon-14 goes through the decay mode where you have this little B and a minus sign. If we then look at table O, we'll see that little symbol, B with the minus sign, is a beta particle. So that will naturally undergo transmutation by releasing a beta particle. All right, so the three types of actual particles that lead from a change of an element into another is alpha, beta, and positron. So these symbols come right off of table O, and they give us a lot of information about the particles. So the top number is always going to be the mass, the bottom number, which is usually our atomic number, but it also represents the charge of that particle. So alpha particle has a mass of 4, the heaviest of the types that we talk about, and also has a positive 2 charge. A beta particle, which actually is the same thing as an electron, doesn't have any mass, but does have a charge of -1. And a positron is very similar to a beta particle, except that it has a positive 1 charge. So all of these particles can get given off and cause an element to undergo transmutation. We already kind of mentioned gamma decay. This is an additional type, but it doesn't actually change the identity of the element because it has no mass or charge. It's just pure energy. So we'll talk about that because that's what makes it kind of the most dangerous or highly penetrating radiation. One thing you have to be aware of that you can see in questions is it will ask about what happens to these types of radiation when they pass through a charged field. And the biggest thing is that you have to know that opposite charges attract and like charges repel. So if I look at this diagram, you have a positive plate and a negative plate. Radiation that goes straight through would be neutral. It's not attracted to either. So that would be gamma radiation. The arrow that goes towards the positive plate must be negative. This is attracted to the positive. So that would be an example of like beta decay would get picked up with the detector in that manner. And then the line that goes towards the negative plate would have been a positive particle because again, opposite charges attract. So that would give us then alpha radiation. So one little thing to kind of pick up on as we start practicing questions in this unit. So a couple of questions just to kind of check in, and you can pause the video and try these out on your own. Positron and beta particles have, and if we look them up over on the side here, we can see the top number. Neither of them have mass, so they have the same mass, but we can see that their charges are different. Beta is -1, positron is +1. So that would be the best answer there is choice 2. Different charges and the same mass. And then number 2 here, which type of reaction can an atom of one element be converted to an atom of another element? This is just the definition of transmutation, so creating or converting to a new element. And then on 3, which nuclear emission has the greatest mass and the least penetrating power? That would be alpha particles. The greatest mass of 4, and it also is the weakest penetrating power out of the 4 that we discussed. And then which nuclear emission has no charge and no mass? That's the pure energy one, which is gamma rays. All right, so make sure you answer those out and write a couple questions if you have them. One last thing that we're going to go through are some things you actually have to memorize about radioactive isotopes. While they can be dangerous, there's also a lot of beneficial uses of radioactive isotopes or radioisotopes. A couple that I put on here that I have starred, you absolutely have to know. So a couple are related to radioactive dating, which you might be aware of from earth science. Carbon-14 is one you have to memorize. That's used to determine the age of anything that was once living. So fossils of animals, plants. Uranium-238 is used to determine the age of geological formations or rocks. It has an incredibly long half-life, so we can use it to measure those types of materials because it's still present in them. The other 3 are all medical applications. You'll find that they all have relatively shorter half-lives because they're interacting with your body, so we want them to be completely eliminated from the body. So the 3 that you have to be aware of is iodine-131. You have to know that that ties into the thyroid. It's used to detect and cure hyperthyroidism. Technetium-99 is related to tumors. They're used to detect them, especially brain tumors. And then cobalt-60 is used as a source of radiation in the radiotherapy of cancer. So cobalt-60 gives off radiation that's used to treat cancerous tumors and so forth. Now, while there's a lot of great benefits, there also are some risks. So any living tissue in the human body can be damaged by radiation. Your body will attempt to repair it, but sometimes it's just too severe or widespread to be repaired. So some of the risks involve like damage to your normal tissue. It can cause mutations in DNA, and now those cells can't function as they normally would. It can also cause illness, such as radiation sickness, and it can even cause death depending on the amount of radiation exposure you get. So just some basic things about alpha, beta, and gamma radiation, and then just some beneficial uses and risks of radioisotopes.